Hi guys, my name is Bernado Santoz. I'm from M7027. I'm your PAL leader for chemistry, and today I was given the Set Khas NSH 2020-2021. It's chapter 2. It comprises of I believe 2.1 and 2.2. So I hope you guys learned something from this. So let's start. So to start, let's read the question. 2a. A photon of light with wavelength 434 nanometer falls in the visible light region and forms a line in the emission spectrum of hydrogen atom. So just by reading the question, I want you to highlight two things. First, the 434 nanometers, because we're definitely going to use it. And also second, the visible light region, because whenever they say or they state in the question explicitly visible light region or ultraviolet light region, that means the first question is most definitely going to be the name of the emission spectrum series. And the visible light region corresponds to only the Balmer series, meaning to say all the visible light region falls in the Balmer series, same as all the ultraviolet light series falls in the Lyman series. And that's an Partian bracket and fun infrared. So whenever they say visible light region, it's definitely Balmer series. So the answer for the first question is Balmer series. So moving on to Roman 2. Determine the transition of electron that corresponds to the above wavelength. So transition of electron means the electron from a higher energy level falls to a lower energy level, meaning to say, or it can be vice versa as well. But in this question, we're going to use the formula 1 over lambda equals to RH in bracket 1 over n1 squared minus 1 over n2 squared in bracket n1 less than n2. So note guys that this is very important. Don't forget to write this. Most of you all forget to write this, and that's the reason you all lose the 1 mark, and we don't want to lose the 1 free mark that they give us, right? So don't forget to write n1 less than n2. So, and another thing that you all should note is that for this specific formula, Rydberg's constant is not 2.18, it's actually 1.097 times 10 to the power of 7 meter per second. Meter. So don't get confused guys. The formula that normally a lot of people use is right here. Energy equals to RH 1 over n initial squared minus 1 over n final squared. So don't get confused guys. If you use this formula, then your Rydberg is 2.18 times 10 to the power of negative 18 joules. But since we are not using this, we don't need to use 2.18. Another tip guys is that if they only give you all energy, meaning to say they give you all only energy, like let's say calculate the energy emitted for the transition, which is in the third question, only then you use the energy formula. Other than that, usually you just use 1 over lambda's formula if they give you wavelength. So just substitute the values inside now. I'll substitute now. 1 over 434 nanometers. I'm going to convert it to meters, and the prefix of nanometer is 10 to the power of negative 9, so you just times 10 to the power of negative 9. It's quite easy to change it. So also guys, another tip is that you can never change the constant, meaning to say Rydberg is the constant in this question, so don't change any value to Rydberg's don't change Rydberg's constant to any other value. Change the other value to Rydberg's constant, meaning to say in this question Rydberg's constant is meter, so we're going to change the nanometer they gave us, which is the wavelength, to meter to match the constant. Only then we can do this question. If I were to write 434 nanometers here without changing it to meter, the answer is going to be wrong. So we're going to equate it with the Rydberg constant, which is 1.097 times 10 to the power of 7, and then 1 over n1. n1 is going to be 2 because Balmer series lowest frequency, the electron in the lowest frequency is 2, so it's going to be 2 squared, and that's why n1 will always be less than n2, meaning to say n2 is the one that we're going to find now, and we don't know from where it dropped to 2 because Balmer series the lowest is going to be 2. So we know from something, maybe n something, n5 maybe, is going to drop to n2. We just don't know what n is it going, from what number it's going to drop to n2. So we're going to write n2 squared here. So solving this, quite easy. Here it's times here, just bring it to the other side, so it will look like 1 over 434 times 10 to the power of negative 9. Since it's times here, just divide 1.097 times 10 to the power of 7. Just use your calculator, guys, no need to be confused. Equals to 1 over 4 minus 1 over n2 squared. So solving this equation, you will get 0.2100 equals to 1 over 4 minus 1 over n2 squared. So after this, solving it is quite simple. This 1 over 4 you just bring there, so it'll be 0.2100. Since it's minus here, since it's plus here, when it goes there it's going to be minus, so it'll be minus 1 over 4 equals to negative 1 over n2 squared. So as soon as you minus this, you're going to get negative 1 over 25 equals to negative 1 over n2 squared. And since there's negative on both sides, just cancel the negative, and it's both sides 1 over 1 over, just flip the equation. So instead of 1 over 25, I flip the equation, it's going to be 25 equals to, instead of 1 over n2 squared, I'm going to flip the equation, it's going to be n2 squared. Now just bring the square there, becomes square root 25 equals to n2 equals to 5. So that's the answer. But don't forget, guys, you have to write electron transitions from n equals to 5 to n equals to 2, because electrons always going to be from a higher energy state to the lower energy state. So you have to write this. Only if you write this, you're going to get the 1 mark. So don't forget to write this, guys. And that's all for Roman 2. So now moving on to Roman 3. Roman 3's question is, calculate the energy emitted for the transition, and it's 2 marks. I'm going to bring the question down for you guys so that y'all can see better. Hold on. Alright. Hope y'all can see better. So Roman 3 is, they're asking you to calculate the energy emitted for the transition. So whenever, guys, they say energy energy emitted, meaning to say in the question there's only energy, very easy. The formula is energy equals to Rydberg 1 over n initial squared minus 1 over n final squared. Quite easy, guys. And in this question, unlike the before one, Rydberg's constant is 2.18 times 10 to the power of negative 18 joules. So don't forget the joules, guys, quite important. Later on you have to put the value in. So to solve this question, very simple, just substitute the values in. So I'm going to substitute the values in now. 2.18 times 10 to the power of negative 18, 1 over n initial. So we know initially it was from 2. From the earlier question we know that it was from 2 and then it went to 5. So the initial is going to be 2 squared minus 1 over final is 5 since we found earlier, so it's going to be 5 squared. So it's very easy, guys. If you all solve the question, you're going to get the answer 4.578 times 10 to the power of negative 19 joules. Don't forget joules, guys. Also, another formula that you can use, I didn't use it here, but you can use also, is E equals to HC over lambda. So you can substitute values here since you have since you're going to find the energy, you have H, you have C, I mean it's constants, and you have the lambda, so you can just substitute in, you'll get the exact same answer. So there's two formulas to this. Use whichever formula you prefer, but do not forget to write joules. Very important, guys. Most of you all forget to write joules. Even I forget to write joules, I mean, I'll be honest, and you guys are going to lose marks for that. So don't forget to write joules. So that's all for question 2a. So moving on now to question 2b. So b, right? All right. So the set of quantum numbers for two electrons with the highest energy of an atom A are shown as below, showing us n equals to 3, L equals to 2, M equals to negative 1, and the spin is positive half, and is the exact same thing below, just the M and the S, the M has an inverse sign, so it's instead of negative it's positive. So the first question is, determine the type of orbitals designated by these sets of quantum numbers. So very easy, guys. Since L equals to 2, I mean it's in the question, L equals to 2, therefore it's 3D orbitals. It's very easy, guys. It's just in any notes that you would open and you would see, you can see that if n is 1, if L is 0, it's either going to be 1s or 2s. If L equals to 1, it's 2p, and if L equals to 2, it's 3d, and if L equals to 3, it's f. So meaning to say 0 is s, 1 is p, 0 equals to s, 1 equals to p, 2 equals to, is the SPDF notation, guys. 2 equals to d, 3 will be f. So since L equals to 2, we know that the orbital is d, meaning to say, I mean it's here SPDF. And how did I get 3? N equals to 3, so it's going to be 3d. If let's say the question said n equals to 4, it's going to be 4d. If n equals to 5, it's going to be 5d, and so on. If L were to equal to 3, instead of 3d, it's going to be 3f. That's all, guys. Very simple. It's just concept question. If you were to understand the concept, then you can do this quite easily. So moving on to Roman 2. So Roman 2 states, name the quantum number that indicates the shape of atomic orbital. So the quantum number that determines that indicates the shape of any atomic orbital is going to be the angular momentum. Angular momentum. Quantum number. Alright guys, very easy, just concept. Moving on. Roman 3 states, write the electronic configuration of atom A. So we know atom A is this top thing, and we know that is 3D. So we know that it's until 3D. So let's just write until 3D first. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d. But you have to understand that 3d has a lot of numbers, right? So like S is going to be 2, P is going to be 6, and D can go up to 10. So if you are wondering what is the number that is going to be on top of D, it's going to be 2. Why is it 2? Because look at the question. They gave us one set and 2 sets. This is the second set and this is the first set. So you can clearly see that they gave us 2 numbers, 2 separate ones. So it's going to be 3D2. If they were to give us 3 separate ones, then it would be 3D3. Very simple guys, just like that. So it's going to be 3D2. So moving on to the last question. Write the electronic configuration of ion A if 3 electrons were removed from atom A. So this is a bit of a tricky question. Even though it's 1 mark, you guys have to read and understand the concept of it properly to actually answer the question. So just looking at this, ion A if 3 electrons were removed, right? So very simple. 3 electrons removed, just remove 2 electrons, remove 1 electron, it's going to be until 4s1. But that's the wrong concept guys, because you have to understand that this is arranged, this top part, usually it's arranged according to this, is arranged according to Aufbau's principle, from the highest energy, from the lowest energy to the highest energy. But it doesn't necessarily mean that it's the valence electron. So you have to rearrange back according to the actual positioning, the actual Aufbau principle that doesn't follow the Aufbau principle, that just follows the number of it for you to actually understand which is the valence electron here. So if I were to write it correctly, it would be, instead of following the highest energy, I'm just going to write it according to number. It's going to be 1, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and instead of 4s2, it's going to be 3d2 first, and then it's going to be 4s2. Because basically what I've done now is arrange this according to ascending number. So just arrange it according to ascending number, so from 1 to 4. And since 4 is bigger than 3, I'm going to write 4 in front first, and then I'm going to read the question. Write the electronic configuration of ion A if 3 electrons were removed. So I'm going to remove 3 electrons now. So if I were to remove 3 electrons, I'm going to remove 2 from 4s. So 4s is gone. I've removed 2 electrons from 4s. And I'm going to remove 1 electron from 3d. So instead of 2, it's going to be 1. So the answer for this question is going to be 1s2, 2s2, 2p6, 3s2. Just copy back guys. 3p6 and 3d1. That's why guys, it's very important for you to rearrange it according to the numbers, for you to know which is the valence electron, and only then can you remove the valence electron in question. So they ask you to remove 3, so you remove 3, and you have to start from 4 because that's the valence electron. If you were to start from 3d2, the answer would be totally different and it would be wrong. And so that's all guys. This is the final answer by the way. So I hope you guys learned something from today. Thank you very much.